Let's talk about a word you hear all the time, acceleration. But what if I told you that you're probably accelerating right now, even if you feel like you're sitting perfectly still? Yeah, it's wild. Let's dig into what this word really means.
I mean, you know that feeling, right? That powerful sensation that just pins you to your seat when a car suddenly takes off or when a roller coaster lurches forward? It's a physical feeling we've all had. Well, that push, that surge, that's the feeling of acceleration. But here's the crazy part. It's happening way more often than you think. In fact, it might be happening when you don't feel a thing. Turns out, acceleration is this constant in our universe, and we're about to see why.
All right, so let's start with the basics, the one everyone thinks of. When you hear the word acceleration, your brain probably jumps to one thing, right? Stomping on the gas and going faster.
And you're not wrong. At its most basic, acceleration is just the rate that your velocity changes. In simple terms, is how quickly you speed up. Think about a car going from 0 to 60, or a sprinter just exploding out of the starting blocks. Their speed is cranking up over time, and that change, that's acceleration.
Okay, but here's where our everyday language gets a little fuzzy. This is where physics throws us a curveball. What if I told you that hitting the brakes is also a form of acceleration?
No, really? Slamming on the brakes is acceleration. I know it sounds totally backwards, but because the car's velocity is changing, even though it's going down, it totally fits the scientific definition. Now, we often call it deceleration, but in the world of physics, it's all just acceleration.
So what's the deal here? It's all about direction. See, when you speed up, the force of acceleration is pushing in the same direction that you're already moving. But when you slow down, that acceleration is pointed in the opposite direction, fighting against your motion. It's the same idea, just facing the other way.
Okay, so we've got speeding up and we've got slowing down. But there's one more piece to this puzzle, and honestly, this is the one that blows most people's minds.
And to get this last part, we have to talk about something called velocity. Velocity isn't just your speed. It's your speed plus your direction. So 60 miles per hour, that's your speed. But 60 miles per hour heading north, now that's your velocity.
And this is where it all clicks. Since velocity includes direction, if you just change your direction, you have changed your velocity. And what do we say acceleration is? Any change in velocity. So get this, you can be accelerating even if your speedometer doesn't budge one bit. Wild, right?
Just think about it for a second. A car turning a corner, even at a perfectly steady 30 miles per hour, is constantly changing its direction. So yep, it's accelerating. A kid on a spinning merry-go-round? Accelerating. And on a huge cosmic scale, our own planet Earth is constantly accelerating as it orbits the sun, because its direction of travel is always changing. So, we've got the what down. We know what acceleration is, but how do we actually measure it? How do we put a number on that feeling of being shoved back in your seat?
Now don't let the formula scare you, it's actually pretty simple. Acceleration is just the change in velocity, that's the little triangle V thing, divided by the change in time. And by the way, that little triangle is the Greek letter delta. In math and science, it's just a handy shortcut for the change in something.
So what is that formula actually telling us? Well, it's basically a measure of how quickly your speed is changing. Let's say a car accelerates at 3 meters per second squared. All that means is that for every single second that goes by, its speed increases by another 3 meters per second. So after 1 second, it's going 3, after 2 seconds, it's up to 6, and on and on.
Okay, let's look at some real-world numbers to see how insane this can be. A Lamborghini can go from 0 to 60 in just 3 seconds. That means it's gaining 20 miles per hour of speed times every single second. But check this out. A cheetah can do the exact same thing. Nature's perfect killing machine accelerates just as fast as a supercar. And even Usain Bolt, coming out of the blocks, is accelerating at almost 7 miles per hour every second. That is just raw, incredible power.
Okay, so we know what it is, we know how to measure it, but what causes it? Acceleration doesn't just happen out of nowhere. There's always something behind it, and that something leads us to one of the most fundamental laws of the entire universe. And that something is always a force. This is the absolute heart of Isaac Newton's second law of motion. Force equals mass times acceleration. You might have seen it as F equals ma. They are fundamentally, permanently linked. You literally cannot have acceleration without a force making it happen. And what's the most common, constant force we all experience every single day? Gravity, of course. Gravity's always pulling on everything around us. And that constant force creates a constant acceleration for any object that's in free fall.
So if you just drop a ball, gravity's constant pull means it doesn't just fall at one steady speed. Oh no, it gets faster and faster and faster the longer it falls. After 1 second, it's moving at a certain speed, but after 2 seconds, that speed has jumped way up. That's constant acceleration, right there in action.
So why don't things just accelerate forever when they fall? Well, because other forces start to get involved. Take a skydiver. They'll eventually hit a speed of about 122 miles per hour. Why? Because at that speed, the force of air resistance pushing them up perfectly balances the force of gravity pulling them down. The forces cancel each other out, acceleration stops, and they just fall at one constant velocity.
So let's wrap this all up. The big takeaway is this: acceleration isn't just about mashing the gas pedal. It is any time an object changes how it's moving, speeding up, slowing down, or just making a turn. It's all acceleration. It's a fundamental part of how everything in our universe gets from point A to point B.
And that leaves us with one last thing to think about. We just saw how the upward push of air can perfectly balance the downward pull of gravity for a skydiver. It's a perfect reminder that motion is always this incredible dance between opposing forces, which kind of makes you wonder, what other unseen pushes and pulls are out there, right now, shaping the motion of everything from the tiniest atoms to the biggest galaxies?